Okay, hi. We're going to read something from I think 19.3, and this is the last portion of 19.3, which begins with a math. So basically, we can start here. It open up soon. It begins with some like complicated math terms, followed by some I think terms that talk about the what is this like the confidence interval. Yes, it deals with confidence interval, so that's what we are going to tackle. Yes, so the first thing, paragraph one, is there anything interesting in the topic math soup paragraph? I labeled it math soup. Answer is no. You can skip it, but we can simplify it in the following way. Top paragraph is just another author doing, so not another, but author doing a formal mathematical proof to satisfy strict academic journals. All it is doing is showing that if you plug an estimated covariance matrix. So what I estimated covariance matrix, probably, I don't know if this is going to estimate covariance matrix with the high. What is this? What is this? This is going to be one of the questions. Into a theoretical chi-square x-square formula. Chi-square Slutsky theorem allows you to swap in sample estimates without breaking the probability math. So what does this mean? I have no idea. Slutsky theorem allows you to swap in sample estimates without breaking the probability math. Ooh, I have no idea. So I'm going to pause and I'm going to take note and then move on. So we have the two things that we want to talk about. I am to talk about with um, Gemini next, which is these two things. What is chi-square and like what is Slutsky theorem? And I have some additional questions about Slutsky theorem as I mentioned here. Now part two, confidence interval. Okay, wait. It is pure backend technical plumbing. Nothing that changes how you interpret or use the model in real life. Okay, glad to know. Part two, confidence intervals for multiple coefficients, building the narrative. All right. Let's bridge what you know from one variable regression to multivariable regression. Number one, it says the single variable narrative 1D line. In one variable regression, a 95% confidence interval for a single slope coefficient B1 beta 1 is a straight line segment. Oh, wait. Oh, on a 1D dimensional number line. Okay. So we are familiar with this one. Standard error and estimated beta 1 standard error. We have like standard error at both ends, and we have an upper bound and a lower bound. It answers we are 95% confident that the true signal coefficient line lies between, not lines. Okay, let me reread this. Reread this. We are 95% confident that the true single coefficient lies between these two numbers. This again. Number two, the multivariable narrative to the 2D ellipse and 3D ellipsoid. Okay. So, so this is the new set of questions that I have from the reading of point two, which is the multivariate narrative through the ellipse and 3D ellipsoid. So I think a starting point would be to see visualize or help visualize how that looks. This is an ellipse, and in 3D it becomes ellipsoid, so it has like three dimension, basically z dimension. So say what happens when you want a 95% confidence interval for two coefficients at the same time, say beta 1 education and beta 2 experience. You can no longer use a straight line. Beta 1 sits on x and beta 2 sits on the y axis. A 95% confidence set for two variables forms excuse me, a 95% confidence set for two variables forms a two-dimensional over ellipse on a graph, which we showed this one. The center of the ellipse, the OLS sample, and I'm like totally forgetting what is an OLS sample, estimates beta 1 and beta 2. Inside the ellipse, all candidate pairs of beta 1 and beta 2 that pass the joint F tests are not rejected. So this line, I am totally in the dark because I cannot visualize how that works, how that would work. I remember from my higher math, there was some rule about, no, I'm forgetting. I'm stretching. I don't want to go there. So I wrote it down that explain this as I cannot visualize it, and added a note that we're using F tests. And I think I miswrote here. I wrote we're running an F test because F tests are how we can learn about both or more than one variables. I think not variables. In this case, at least, on coefficients associated with the experiment. I think the wording needs some work. How about that? Why is it shaped like an oval ellipse instead of a square box? I think it is kind of self-explanatory because education and experience are correlated. If you estimate your education, sorry, if your estimate of education's effect goes up slightly, your estimate of experience's effect usually adjusts downward to compensate. Wait, what? If your estimate of education's effect goes up slightly, we're testing something, education's effect is going up slightly. Your estimate of experience's effect usually shifts or adjusts downward. The tilt of the oval usually captures this correlation covariance between the two variables. Okay, I'm going to take their word for it currently. Part 3, we have breakdown of the equation 19.29 and the new symbols. It is the exact formula for the last paragraph, from the last paragraph. So the last paragraph here is the one we saw in book. So we have, I'm forgetting what is this, lambda? Is this lambda? Delta, excuse me, little Greek delta. So the big one is a triangle, little one is this. Delta equals delta. What is this, like epsilon? Or sure, they're going to break this down. So let's translate every new symbol into standard plain terms. Delta, what it is, what it is, a vector representing the target subset of coefficients you want to build a confidence interval for. Okay. Example, if you only care about building a joint confidence set for beta 1 and beta 2, out of 10 total regression variables, then Q equals 2. Okay. I think we know what that is, right? And delta had, what it is, the sample estimate of those specific coefficients calculated by OLS from your data set. Sample estimate of those two specific coefficients calculated by OLS from your data set. So this is like the result we got. The distance, the vector gap, it measures how far any candidate point delta on your graph is from your actual OLS data estimate delta hat. Number 4 is the critical value, what it is. The cutoff number from F distribution table. In one variable regression, your cutoff number was 1.19 from the standard normal Z distribution for a 95% confidence interval. In multivariate regression, your cutoff number is C, which is the 95th percentile critical value of the F distribution. Okay, instead of again Z distribution, we are dealing with F distribution, and if I'm not getting it wrong, we have T distribution when there is we have lower samples. Okay, so we can use Z distribution. We have more than, I guess, 30 samples. We have less than that. For one single variable, we can use T distributions, and I think for one variable tests F basically means T square, and F is also associated with R square. We know from basic cursory finance the relationship of R square, which is capturing like how effective was the test, like it is like the regression that we just ran, did it explain, or how much of the entire thing it explained? So what we do in finance, we take like one company and we run a regression test with the entire market. So say the R square gives you 75%. Okay, that means 75% was, I think, and I could be getting it wrong and I need revision. The market was explaining 75% of the data, or like the fluctuation. Market was explaining 75%, and the rest of 25% was basically internal to the company. I think we were like in there, we in regression we were like measuring volatility, so that could be a thing. Anyways, reading equation 19.23 in as one plain English sentence. The 95% confidence set is the collection of all candidate coefficient pairs delta whose distance from our sample estimate delta hat produces an F statistics that is less than or equal to the critical cutoff value of C. So this thing, which I just wrote, is again yet again another a difference of error terms and the corresponding value in like F statistics. We are like minimizing error again. A note to myself again, in finance what we're trying to do is we are trying to minimize errors. So when we have a gap of errors and we have a corresponding value for that in the F statistics, then we can like directly compare with the value of C. And I think the assumption baked in here is also that this is a bell curve. So summary table one variable, summary table one variable versus multivariate confidence interval. Features: single variable 1D and 2D. Shape: line segment, we knew that. Oval and ellipsoid. Single estimate, vector point, beta 1 and beta 2. Do I need to get that much into like why is this a vector point? Not now. We will leave it for now. Critical cutoff is 9.1.96 C distribution, and for critical cutoff in F distribution is 95th percentile. Test formula: T statistics is less than 1.9 and F statistics is like less than C. More options, but I think I'm happy with this recording so far. Let's see how it works. I probably should revisit this after a week just to see how it worked, how it sounded, and how much I retained.